Welcome to Lecture 7 of our Object-Oriented Programming course. Today, we begin a vital topic that distinguishes resilient applications from fragile ones, exception handling in C#. As your programs grow in size and complexity, errors are inevitable. What matters is how we deal with them. This lecture will give you the tools to detect, handle, and recover from runtime errors in a clean, controlled, and professional way. By the end of this unit, you'll understand how to identify and handle runtime problems using C#'s exception handling framework. Our agenda includes the concept of exceptions, how to use try-catch finally blocks, how to throw and rethrow exceptions, custom exceptions, and key best practices. Let's begin with the fundamentals. An exception is an event that interrupts normal program flow. It typically arises due to unexpected conditions like division by zero, null references, or file access errors. Instead of letting your application crash, exception handling provides a way to gracefully manage such issues. Let's look deeper into causes and consequences. Causes can be logic errors like dividing by zero, memory issues, or bad user input. Consequences include program crashes and corrupted user experiences. Handling exceptions means we take control of failure scenarios and ensure our application behaves predictably, even when something unexpected happens. C# and the .NET framework provide structured tools for exception management. Try holds the code that might fail. Catch deals with specific or general exceptions. Finally, runs cleanup logic regardless of what happened. Throw lets you raise your own exception. Together, these keywords give us the structure to control errors, log them, and recover cleanly. Exception handling is a programming discipline that helps us deal with unexpected runtime errors. Examples include trying to divide by zero, accessing an index that doesn't exist in an array, attempting to open a file that isn't there. Instead of allowing such cases to crash our program, we use exception handling to catch and handle them appropriately. Let's clarify the roles of each construct. Try encloses risky code. Catch blocks specify how to respond to each exception. Finally guarantees cleanup like closing files or releasing memory. Throw is used when you want to raise an error intentionally. These are your tools for writing safe, stable, and responsible code. A try block protects code that may throw exceptions. Once an exception occurs, execution immediately exits the try block. The remaining lines in it are skipped. This is why we place only risky or essential code inside try, and let the rest be handled cleanly in catch and finally. Here's the general structure of a try-catch finally. Always start with specific exception types, then add a generic one at the end. The finally block is always executed, making it ideal for releasing resources like files or database connections. Some exception types you'll encounter frequently. System.exception, the base class for all exceptions. Format exception occurs when parsing fails. Divide by zero exception happens when the denominator is zero. File not found exception if a file doesn't exist. Index out of range exception if you access an invalid array index. Knowing these helps you handle exceptions precisely and appropriately. This example shows how to handle multiple exception types. First, we try parsing a number and dividing. If parsing fails, we catch format exception. If division fails, we catch divide by zero exception. Any other unexpected error falls into the final generic catch. This layered handling makes our code robust and informative. Let's wrap up this section with the essentials. Always use try-catch finally to control failures. Catch specific exceptions first, then general ones. Use finally to ensure that resources are released. And never assume that nothing can go wrong. Assume it will and prepare for it. These principles help you write error-resilient applications. C# treats exceptions as objects, and exception handling is fully object-oriented. All exceptions inherit from the system.exception class. You can even define your own custom exception classes to handle domain-specific errors in a structured way. Here's the hierarchy. System.exception is the root. Built-in runtime exceptions inherit from system exception. You can create your own by inheriting from application exception or exception. This structure provides a flexible and organized way to handle both standard and custom errors. Why bother creating your own exceptions? Because they allow you to communicate clearer, more domain-specific messages. For example, a user not found exception or insufficient balance exception tells you exactly what went wrong. Creating a custom exception is simple. You extend the base exception class and pass the error message to its constructor. Once defined, you can use your custom exception just like any other. Use throw new myException to raise it. Catch it with a specific catch, myException block. This way, your application logic stays clean, expressive, and modular. To recap this first part, C# uses object-oriented exception handling. You use try, catch, finally, and throw to manage failures. You can define your own exceptions to improve clarity and control. Now let's see these concepts in action with real-world examples. Here's a short program that catches both format exception and divide by zero exception. It first asks the user for two numbers and divides them. If the input isn't numeric, it catches the format error. If the second number is 0, it catches the divide by zero error. This demonstrates how to write user-friendly and crash-resistant programs. So why should we handle exceptions? First, to avoid program crashes. Second, to allow the program to recover or retry. Third, to ensure resources like files or memory are cleaned up. Good exception handling is the foundation of fault-tolerant applications. This simple console application calculates miles per gallon. The version without exception handling crashes if the user types a non-number or enters 0 for gallons. In the improved version, we add try-catch blocks to manage input errors and division by zero. This results in a safer, more user-friendly experience. Here we have a basic program that calculates miles per gallon. The user is prompted to enter two values. This version is functional, but fragile. There's no protection from invalid or dangerous input. In production systems, this is unacceptable. Now we've improved the program by introducing exception handling. The input and calculation are enclosed in a try block. If the user types non-numeric input, the convert.2and32 call will fail and throw a format exception. This is caught and handled with a friendly message. Please enter numeric values. If the user enters 0 for gallons, division by 0 triggers a divide by 0 exception, and we inform the user cannot divide by 0. This version is significantly safer. Instead of crashing, the program guides the user to correct their input. This is a key step toward writing user-resilient production-grade applications. This example shows the evolution of robust error handling and highlight why exception handling is essential in every professional application. Finally, let's talk about resource cleanup. Even if your program throws an exception, the finally block will execute. In this file handling example, we ensure the file stream is closed no matter what happens. This is how you protect your system from leaks or locks. Let's conclude this part with the essentials. Use try-catch finally to protect against runtime errors. Handle different exception types separately. Use finally for cleanup, especially for files, connections, or external resources. Never trust user input. Always validate. These are the fundamentals of writing reliable and professional C# programs. You've now seen how exception handling works from both a technical and design point of view. In the next part, we'll take this further and look at advanced techniques, rethrowing exceptions, nesting try-catch blocks, and building exception-safe components. Let's keep building toward clean, maintainable, and production-ready code.